Hello viewers, in today's session we are going to discuss another important functional equation, right? And here in this session we are going to discuss this functional equation where we have f of xy is equal to xfy plus yf of x for all values of x and y belonging to the set of positive real numbers. And here an additional condition is also given, that is f of x is differentiable in this interval that is from 0 to infinity, and we have to find out the function f of x. So here we'll solve this functional equation with the help of derivatives, right? So we'll use the method of partial differentiation to get the value of f of x. So we are given the functional equation, that is f of xy is equal to x f of y plus y f of x for xy greater than 0. And remember, here x and y are not equal to 0. Now we'll differentiate this functional equation both sides partially with respect to x. So differentiating partially both sides with respect to x, will get d by dx of f of xy, and here we have del of del x x fy, and here we have del of del x y f of x. Now here we have f prime of xy, and by chain rule we have to differentiate this product, that is xy. And here when we are differentiating partially with respect to x, then y is treated as constant. So we have simply f of y outside this operator, and we have del by del x of x, and here we can take y in front of this operator, and we have del of del x of f of x. So now here we have f prime of xy, and the derivative of this product xy with respect to x is simply y, because the derivative of x with respect to x is 1, and here this quantity is 1, so we have f of y, and here we have y times f prime of x. So this is our equation number 1. So now this equation 1 is going to be very important in getting the solution of this functional equation. So here what we will do, we'll replace y by x and x by 1, right? So replacing y by x and x by 1, let us see the changes in equation 1. So we have f prime. Now we are replacing x by 1. So here we have 1, and y by x, here we have x for y, and here also we have x, and here we have f of x, and here we have x, and here we have f prime of 1, right? So now we can also write this equation as x f prime of x, and here we have f of x plus x f prime of 1, and let us call this equation as equation number 2. So here we see that we have f prime of 1, that is the derivative of f of x at x is equal to 1. So let us take f prime of 1 as a. So now we can write equation 2 as x f prime of x, and here we have f of x, and here we have ax. For f prime of 1 we have written that is a. So we have now this equation. So now let us call this equation as equation number 3, right? Now let us consider the derivative of f of x over x, right? So we can take the derivative of f of x over x, and then we'll connect this derivative with this equation, right? So here applying the quotient rule for the derivatives, we have x, then we have f prime of x, and then we have f of x, and the derivative of x is 1, and in the denominator we have x square. So here we have used this result, that is, if u and v are functions of x, then the derivative of this quotient is given by v du over dx minus u dv over dx divided by v square, right? So here from this equation we can now write dy dx of f of x over x is equal to x f prime of x minus f of x divided by x square, right? And multiplying this derivative with x square, we have x square dy dx of f of x over x, and taking this term to this side, we have f of x is equal to x f prime of x, right? So now substituting this value of x f prime of x in equation number 3. So now equation 3 gives us, for x f prime of x, we can write this expression. So we have x square d by dx of f of x over x, and here we have f of x, and here the right hand side is f of x plus ax, where a is f prime of 1. So now we can cancel out these two terms. So we are left with x square d by dx of f of x over x, and here we have ax, right? Now see here, this x and this x get cancelled, because we have already assumed that x and y are not equal to 0. So we can cancel this x with this one. So we are now left with x dy dx of f of x over x is equal to a. Now taking this x to the denominator of a, we have dy dx of f of x over x is equal to a over x. Now integrating both sides with respect to x, right? So here we have dx, and here we have c as the constant of integration. So now in the left hand side, the integral of d by dx of f of x over x is simply f of x over x, and here we have a integral dx over x plus c. So now we can write f of x over x is equal to a, and this is equal to the logarithm of x, and c is the constant of integration. So now let us multiply both sides by x. So we have f of x is equal to ax log of x plus cx, right? So this is our function f of x. So now let us find out the value of this constant of integration c by using some initial condition. So from the given functional equation, we can write, if we take x is equal to 1 and y is equal to 1 in this equation, then we have f of 1 times 1, then we have 1 f of 1, and then we have 1 f of 1. So this is simply f of 1, this is f of 1, and this is also f of 1. So from this equation we have f of 1 is equal to 2 times f of 1, and solving this equation we have 2f of 1 minus f of 1 is equal to 0. So f of 1 is equal to 0, right? So this is an important condition, that is the value of the function at x is equal to 1 is 0. So we'll use this condition to find out the value of the constant of integration. So now taking x is equal to 1 and f of 1 is equal to 0, in this equation we have f of 1, then we have a 1, and this is log of 1, and here we have c times 1, right? Now f of 1 is 0, and here we have a, and log of 1 is 0, and here we have c, so this is simply c. So the value of the constant of integration c is 0. Now let us substitute this value of c in this equation. So we have f of x is equal to ax log of x. So this is our required function.